Hello, so this is a graph. It shows a force extension relationship. So the question is saying Fig 1.1 shows a force extension graph for a spring. So obviously when you come across something like this, you know it's definitely talking about this guy, right? Hooke's law. Hooke's law, right? On the vertical axis we have force, and then on the horizontal axis there is extension. The force is in newtons and the extension is in meters. No prefixes there on both axes, so we are good. Right, let's look at what part A is saying. Right, the question is saying calculate the spring constant K of the calculate the spring constant K of the spring. Right, so each time when you're given a graph like this, which is a force extension graph, the gradient of this line will always give us the spring constant. All right, but then if it was extension versus force, then the gradient of the 1 over gradient of the line will give us the spring constant. So from Hooke's law, why am I saying so? We know from Hooke's law that F is equal to KE, E for extension, right? So in our case, if I put delta on F, delta F is equal to K delta E, right? Which means K is equal to delta F over delta E. And delta F is actually change in the y-axis, and delta E is actually change in the x-axis. Anything that gives us change in y over change in x will always be equal to gradient. Alright, so in our case, for us to get the K value, we are simply saying K is equal to change in F over change in extension. So we can pick any two points on the line. So I'm going to take the most convenient points on the line, right? So I think if we take 0, 0, 0, 0, and that one up there, which is 0.10 and 5,000, it will be ideal, right? Which means this is probably our x1, y1. This is our x2, y2. So remember, when you're calculating gradient is change in y over change in x, I can have y1 minus y2 over x1 minus x2 down there. So this is simply equal to 5,000 minus 0 over 0.10 minus 0. Right, what do we get from here? This is simply 5,000 divided by 0.10. Right, 5k divided by 0.1. Right, I'm getting 50,000. Right, this is 50,000 newtons per meter. Yeah, 50,000, sorry, not 5,000. So the value of K is 50,000 Newton per meter. One can turn this into 50 kilonewton per square meter. Is still okay. So on a force extension graph, the gradient of the line will always give us the spring constant. Okay. Now let's see what part B is saying. A student states that the spring has not reached the limit of proportionality when a force of 4,500 newtons is applied to it. State how the graph shows that this statement is true. Right, if you look closely on the graph, you can see that when a force of 4.5 is applied, right, 4.5 is somewhere there. That's where 4,500 is, right? It's actually corresponding to a value down there on the x-axis for my extension. So you can see at this particular point we still have a straight line, and that straight line passes through the origin. So as long as we still have a straight line at that particular point and it's passing through the origin, it means we're still obeying Hooke's law. We haven't reached the limit of proportionality. So this is how the graph is showing that we haven't reached the limit of proportionality. So the student is very correct by stating that the graph hasn't reached the limit of proportionality when a force of 4,500 newtons is applied. State how the graph shows that this statement is true, right? So you can say the graph is still a straight line and passes through the origin. If the graph wasn't passing through the origin, we'll be having issues there. And if the graph was not yet a straight line, was no longer a straight line, then it was not going to definitely satisfy Hooke's law. Remember, this graph can go all the way and look like this. So if you have extension this side and force that side, the graph is a straight line for a certain period of time until we go beyond. Limit of proportionality is usually represented by E. Right, so within this region from here to there where there is a straight line, that's where Hooke's law applies. Then after that, the graph will usually bend towards the extension axis. This is where we have elastic limit and probably plastic deformation, depending on how far the wire or the spring has been stretched. Okay, yeah. So as long as it's still a straight line, then it means we still obey Hooke's law. Right, I hope you remember that from your notes. Right, springs can be compressed by forces. Now, the spring described by Fig 1.1 is compressed by a force F and has an extension of minus 0.025 meters. Determine the force. So extension can be positive or negative. If extension is negative, it means we are actually compressing the spring. If it's positive, it means we are stretching the spring. So in our case, we are going to use Hooke's law. We know that F is equal to KE. We already found the value of K as 50,000. Remember, 50,000 newtons per meter. So it's just a matter of substituting here, right? It means with 50,000 times minus 0.025, right? This will give us what? So 50,000 times 0.025, right? I'm getting 1,250, negative 1,250 newtons, right? But then if you look at our raw data values, you realize that we have two significant figures there, so we can round off our value to two significant figures, minus 1,300 newtons. So that this negative sign is clearly indicating that we have a compression. So it's still okay to write it as minus 1,300 newtons, because the negative sign implies that it's negative extension, like it's compression, right? Yeah, I hope you get it. So this is how we calculate this one. State whether force is a scalar quantity or a vector quantity. Explain your answer. Of course, this is now different from this whole thing of Hooke's law. Definitely, a force is a vector quantity. Vector quantity. Why do we say so? Because a force has both magnitude and direction. So any quantity that is magnitude and direction, we call it a vector quantity. So a force is a vector quantity.